let me think back through my train of thought. Oh, as I had promised last time, but I didn't get posted until today, I put the Chapter 14 questions for homework under quizzes on Springboard, and it is due on November 26th at 5 p.m., so I wanted to give you at least a week to do it. And then the quiz grade that will count as 10 points will be submitting your notes from the last class on 11/18. So in the Dropbox on Springboard, you will be able to see. I put a Dropbox. You can either submit your notes as a PDF if you scan them, or if you take them in Word or something like that, or you can take pictures of them with your phone and submit them as a JPEG. Make sure that you're thorough and that you show me that you are actually keeping up with the material. So those two assignments right there under homework and notes, so under quizzes on Springboard is where the homework is, and in the Dropbox is where the notes go. So I want to make sure I don't confuse you. Yes?
You only want that one day, the notes from that one day?
Yep.
Okay.
Yep. Any other questions?
Can you repeat that? Notes go on Springboard?
Notes go in the Dropbox on Springboard, and the homework is Chapter 14 under quizzes. Cool? Those should be relatively easy points for you, I hope. What else do we have going on here today? I will get to this. This is a funny one. So we are going to pick up where we left off the last time. We were talking about life histories, which are basically the strategies for population survival in particular environments. So humans have a different strategy for survival than mice have. A giant tortoise has a different strategy than a hummingbird has. So what we do is we look at these things that are called life histories, and these weren't actually figured out until about 100 years ago when insurance companies started offering insurance. They came up with life history so they could figure out how long people were going to live, and then once they calculated how long people were going to live, they offered them insurance for just enough time that the insurance company could make money without paying out on those claims. And so they then took this, biologists latched onto it and said, oh, we can do this for any species. So we're going to look at some different strategies for survival. And there is an animal that actually mates itself to death, like we had kind of talked about with the bush cricket. Here we have what is called antechinus. It is a small mouse-size, looks like a rodent, but it's a marsupial. It reaches sexual maturity at 1 year. So a 1-year-old antechinus is capable of reproducing. And then at 1 year old, it mates intensely for over a 3-week period, and it will basically do it for about 12 hours at a time. And then once that 3-week period is over, the male deteriorates and dies. And so imagine if that happened in humans, that after the first time that a male human had sex, he would do it for 12 hours at a time, and then 3 weeks later would die. That would not go over very well with the ladies, I don't think. But this is something that allows him to have the most offspring that are going to be born and carry on his genes and be able to survive. So what we call that is Big Bang reproduction. Then we have another creature, the greater bulldog bat. It's about the same size, but it goes through a whole different variety of reproductive investment. So he reaches sexual maturity at 1 year, and then he produces about 1 offspring per year and can live to be about 33 years old. So whereas our antechinus is going to live to be about 1 year and 3 weeks, the greater bulldog bat, that's basically the same size but living in a different environment, reaches sexual maturity at the same time, but has a much different reproductive investment than the antechinus does. And then we have our common house mouse that you might see in anybody's house. We've got our fast, intensive reproductive investment. So the common house mouse is going to reach sexual maturity at about 1 month. So unlike the other two who reach sexual maturity at 1 year, he reaches sexual maturity at 1 month. And he produces litters of 6 to 10 offspring every month and may generate more than 100 offspring in its first year. But the chance of him making it to a year old is very, very slight. And so whereas the bat makes it to 33 years old, he may make it to only a year. So fast and intensive mating, and it puts in this initial reproductive investment that's different than the other two. So why do we have all of this variation? We might ask ourselves, is this one strategy better than the other evolutionarily? And the answer is, one strategy never fits all. There's never just one way to solve a problem of reproduction. So in different environments, in different populations, in different places around the world, we have come up with lots of different species of organisms that have more than one way to solve a problem. So in meeting those possible challenges, it may respond by reproducing in a different manner. It may change how often it reproduces, or it may change how much it reproduces, or at what age it begins reproducing. So the life history of an organism is a vital statistic about this species. It's something that we need to know in order to understand how these species work. So the life history of an organism includes the age at first reproduction, its probability of survival and reproduction, because if you think about the bat has a much greater chance of survival than the mouse does because everything eats mice. And so the probability of the mouse's survival is not very good, and the probability of the bat survival is very good. We have reproduction at different ages. We have litter size. Are you going to have 1 baby at a time, or are you going to have 12 babies at a time? And then frequency. Is it going to happen once a year, or is it going to happen once a month, or is it going to happen once a week? And so then how long does the organism live? Does it live to be a year old? Does it live to be 5 years old? Does it live to be 33 years old? So these are complicated questions. And so the first thing that we look at when we are looking at organisms is we look at their reproductive investment. We look at the material and the energetic contribution that the individual will make to its offspring. So how much energy do you have to put into producing these offspring? Are you putting a lot of energy into a single egg, or are you not putting very much energy into a lot of sperm? Are you putting energy into gestation, which means pregnancy, or are you putting your energy into releasing eggs? There's lots of different things. How much energy do you spend in order to make these offspring? So is a single episode of reproduction better? If you think about humans, humans may only have 1 child, or is it better to have repeated episodes of reproduction? So like the common house mouse, that may produce 6 babies every month. So also happens in plants. It's not just animals. If any of you are gardeners, or you like to grow your own vegetables, you know that there are some that are annuals and some that are perennials. There are some that you're going to have to plant every year from new seeds, and there are going to be some that will last a long period of time and will produce fruit each year. So plants as well as animals put energy into reproducing. And so which life history strategy is best? What we really need to look at is what environment is it surviving in? What is the cost of reproductive investment during any reproductive episode? So how likely is it that you might be killed or eaten during a reproductive episode? How likely is it that you will live a long period of time and be able to reproduce again? So what's your likelihood of survival? And what we look at here is natural selection. So nature kind of shapes the way that we have these lifetime reproductive successes. So humans put off mating so much longer than cats or mice because we are at one extreme of the life history. We wait a long time, sometimes 2, sometimes 3 decades before reproducing, and then we live a very, very long life. And generally, we just have one offspring at a time. Now with in vitro fertilization and things like that, we're starting to see more episodes of twins and triplets and quadruplets. But generally, humans are just having one baby at a time, and they're waiting longer to have it. Cats don't live as long as humans, and they have babies much sooner. And then mice don't live as long as cats, and they have lots of babies much, much sooner. So how likely is it that they will be able to survive and reproduce and make it to the next year to have another litter? So when we're describing these populations, we do so quantitatively, basically using numbers in life tables and looking at the way that we graph those survivorship curves. And so here's an example of like what the insurance people were looking at with a life table in humans. If we have the age at the beginning of the interval, well, this wouldn't be humans because these numbers are a little bit off. But imagine that the age at the beginning of the interval, there's 210 alive, and that means we have a 1%, so 210 out of 210. And then during that interval, usually a year, we've got 140 that are left. So the probability of you dying during that time is 67%. And then if we get to 3 years, we've got 70 that are still alive, so the proportion that are alive are 33%. 28 more die, so you have a 40% probability of dying during that interval. So notice, as we go up in the number of years, the greater the likelihood is that you're going to die. That should make sense to you. As far as humans go, most of our 0 to 10-year-olds are going to make it, and then your chance of 10 to 20 is going to be a little bit higher that you might die. The chance of 20 to 30, a little bit higher that you might die. Chance of, imagine if you get up to 60 to 70. We're starting to get up to the age in humans where it's going to be more likely that you're going to die. And so if we get up to 100-year-olds, that proportion that are left is very, very small. So we're going to look at the way that we have these survivorship curves, and we can predict how likely it is that you're going to die. And that sounds kind of awful, but we'll continue through this. So these graphs of the particular age of individuals that are still alive in a population. So starting up here with our giant tortoises, if you imagine where a giant tortoise lives, it doesn't have too many natural predators. It's pretty good at being able to survive, bless you, because they will very likely survive until old age, rapidly decreasing the survivorship. So what we see happening here is that we've got lots of them surviving, and then as we start to get up in age, more and more of them are going to die off until we get to the most furthest upper age, and then most of them are going to be dead. And then if we have our bird right here, the survivorship decreases at a steady rate. So it's not more or less likely that it's going to die during any particular age, but the survivorship is just going to go down at a steady rate. And then we get to these poor mackerel, and they have a high mortality rate early in life because as they hatch, lots of things love to eat them. But those that survive in those early years are going to live a long life. So what happens is most of them die really, really fast, and then the ones who do make it are going to live a very, very long life. So 3 different ways of looking at your ability to be able to survive. So which one do you think that humans are most like? Yeah, we are most like the giant tortoise. We don't have too many predators. The chance of us surviving is pretty good until we get to old age, and then eventually everybody dies. So there are trade-offs between reproduction and longevity. The trade-offs in energetic investment, in the variety of ways that we reproduce, and in what happens to us as we age. So when we think about designing organisms for different environments, we look at these life histories and maximum fitness. Maximum fitness not being the strongest, but being the most possible way, the highest possible way to have the most number of your offspring survive. So we have these trade-offs between producing many offspring or producing few offspring. Do we do it as soon as we are born, or do we wait until later in life? Does it continually happen every year, or does that start to taper off? While growing tremendously large, do they reduce the predation risk? So think of like our big mammals, our elephants, our giraffes, our buffalo. They're going to have one baby at a time because they're going to reduce the predation risk by taking really good care of that one offspring that they have. And then nothing lives forever, so at what point is it going to perish? So evolution has caused some constraints here. All of those traits are not possible. Things do not live forever. Things don't have unlimited number of babies. Things don't have unlimited amounts of energy. So the selection for that particular environment is going to cause one or the other of those traits to adversely affect one another. So there are basically evolutionary trade-offs. What is going to maximize your success in the environment that you're living in among these different traits that we looked at before? So at the ends of each of the spectrum, and then everything that's in between. So the three areas in which an organism can allocate its resources, so the three possible ways that we can go about this here is we can vary the amount of growth, vary the amount of reproduction, or vary the amount of survival, or the length of survival. So looking at our salmon, Big Bang reproducers like that little shrew-like creature and a salmon, they are going to grow exponentially during that first year. And once they reach that year age, then they're going to put all of their energy into reproduction, and they go through that one single Big Bang event, and then are going to die shortly afterwards. So if you've ever seen a documentary about Alaska where you see the salmon, and they're all rushing around and they're jumping up the stream to try and get up, and the bears are eating them, the really awful thing is that right after they spawn, then they all die. And so the edges of the shores of these rivers are just littered with these dead salmon because they've made one giant reproductive investment, and then that's it for them. So here we have beech trees, and they are going to grow much more slowly during the years when they produce a lot of seeds. And then in the years that they are producing few seeds, they will grow a lot. So they have traded off between reproduction and growth. So in the years that they grow a lot, they don't produce seeds. In the years that they don't grow very much, they produce lots of seeds. And so I don't think that we usually think about these when we think about, we don't usually think about plants, or at least I don't. I usually think about what's happening in the animal kingdom. But here, another one, number and size of offspring. So these female lizards produce medium-sized eggs as a compromise between many small eggs with a poor survival of offspring and a few large eggs with a better survival of offspring. So this is similar to what we talked about with humans, where human babies that are right about 8 pounds are going to be the most likely to survive, and the ones that are really, really tiny, they have a small chance of survival, and the ones that are really, really big have a higher chance of killing the mother. And so trading off between the number and the size of your offspring is going to change your ability to have those offspring be able to survive. So in looking at the ecology out there, this is going to influence the evolution of aging in a population. So now we're going to look at what does it mean to get old, which is something I don't like to think about. Naturally, when things get older, they are going to begin to fall apart. And so this is basically the gradual breakdown in a body's machinery. The healthy, successful 10-year-olds or teenagers, I mean, you may think back to your teenage years and think, man, I was so awesome when I was 16, or I was so great at 25, and then what happened to me when I turned 30 or 40 or 50? It's because your body is going to gradually wear down as you use it. And so this is a really cool picture because this was a group of classmates that had a picture taken of them, and then when you look at them as they age, it doesn't appear like they really changed all that much at all. But aging is simply an increased risk of dying with increased age. If any of you have ever noticed, like, you hear of your classmates and you may think like, oh, I've heard of one or two of the people I went to high school with pass away. And then as you start to get into your 30s, you hear about more people passing away. As you start to get into your 60s, you hear more and more people are passing away. And aging is simply the increased risk of dying with increased age. So why do organisms have to age? Is there a reason that that has to happen? The force of natural selection is going to lessen with advancing age. So what that basically means is that a lot of the genetic diseases that we have out there, if you imagine like heart disease or certain types of cancers or diabetes, these genetic diseases kill older people, but almost none of them kill children. And the reason behind that is that if you are an infant and you're born with a gene that causes death at the age of 10, then if you die off at age 10, you do not reach sexual maturity. You do not pass those genes along to your offspring. And so those genes are going to be weeded out very quickly because they almost never get passed along. But in alleles that cause sickness and death later in life, if you have an infant born with a defective gene that causes it to die at age 150, then they reach sexual maturity. They go on to have babies. They go through their reproductive investment, and then they almost never reach 150. And so same thing happens. That's why a lot of our genetic diseases seem to hit people in their 60s and their 70s, because they've already gone through reproducing and they've already passed those genes along to their offspring. And so mutations that arise and cause their carrier to be more likely to die later in life, mutations like those that increase the risk from cancer or from heart disease or diabetes, other types of ailments, you're going to see those popping up in the 40s, 50s, 60s. And they don't affect the reproductive output because people have already sexually matured a lot earlier than that. So those diseases can almost never be cleaned out of a population. There's no way to get those genes out of the population because people have already reproduced and passed those genes along to their offspring. And so we might at some point be able to find a cure for cancer, but we're never going to be able to have a cure for aging. This is kind of the fountain of youth type of idea. There is a difference between curing diseases and curing getting old. So what is going to determine how long you're going to actually be able to survive? Among humans, we may just think of genes. Among the animal kingdom out there, we might think about predator-prey relationships. How likely is it you're going to get eaten? We might think about lightning. How likely is it that your environment could be destroyed by fire? Drought. How likely is it that you might starve because there's no plants? Or different types of diseases. And so we have two different types of worlds. Just like when we think about humans and first world countries versus third world countries. In high-risk worlds, the death from external sources is very, very high. So they tend to reproduce very, very early. An example of this would be rodents. The chances of them being caught by predators is really, really high. Everything loves to eat rodents. And so they have to reproduce very early in order to keep their numbers going. But then in low-risk worlds, like with the giant tortoises, death from external sources is very low. So almost nothing is going to kill a giant tortoise. And so it is going to wait to reproduce until it's a little bit more stable and ready to be able to do that. So the age at the time of reproduction is a key factor in determining longevity. So if you think about humans, we may be ready to technically reproduce at age 13 or 16, but the longer we wait, the more likely our children are to be able to survive and make it to old age themselves. And so if you have reproduction very early in a life cycle, it will also favor early aging. So in populations that we see where they are reproducing very early or early in their lifetimes, we're also going to see them dying off a lot faster. So the later reproduction is put off, that will also favor later aging. So here's those two examples again. The rodent, which we call the Snickers bar of the desert, likes to be eaten by everything. It has a relatively high risk of dying at every age. And so the individuals have to reproduce earlier. Therefore, they're not going to live as long as a giant tortoise, and they're going to have shorter lifespans, maybe 1 or 2 years. In a low hazard factor environment, they have a low risk of dying at each age. The individuals are going to reproduce later in their life, so reach sexual maturity later. They also have later aging, so they may live to be 150 years old, and they have these longer lifespans. And it's just due to what type of environment they are living in. And so in environments that are characterized by low mortality risk, low risk of dying, populations age very slowly. And if they have a high mortality risk, the exact opposite is going to happen. So can we slow down the process of aging? We have absolutely shown that that's a possible thing. Life extension is possible. It used to be that humans made it to 40 years or 50 years old. Now we hear about people living to be 100 all the time. And so life extension is definitely possible. If you remember back to our fruit fly experiment where we let them live in this cage and then took away the food, and the ones that made it the longest, we bred them together, and they were able to live longer. And then we wait until almost all of them are dead and take those and breed them together, and those are going to live even longer. So we've seen this happen in the laboratory. We've seen that we go from an average age of 33 days, 10 weeks later we have an average age of 63 days. So over many generations of selection for later and later age, the average lifespan in this case of fruit flies has actually doubled. So we see this in human populations. We're always trying to find the next big thing that's going to allow us to live longer. But the unfortunate thing is we don't always live longer without those health complications. So the longer that people live, the more often that we see that it's not a great quality of life at the end. So we're looking this week in the lab at age pyramids and what happens with things like the baby boom, what happens in first world countries versus third world countries, and talking a little bit more in depth about the baby boom. If any of you know anything about the history of the United States, right after World War II, I believe it was, or right before World War II, a lot of people knew that their husbands were going off to war, and so they had a lot of sex, and the women got pregnant, and so they had this huge population of babies that were born right after these men all left to go to war. And so this is what happened with the baby boom. You often see these big families. And so what this looks like, oh, let me get to this one. No, this is Norway and Kenya. Here's the United States with baby boomers. So we see here at the bottom of the pyramid, we've got age of 0 to 4, here are our baby boomers as they were growing up in the 1980s. And so we had this huge outcropping of baby boomers. And think about all the resources that we had to put into the baby boomers in order to allow them to live here in the United States. We needed more teachers, we needed more hospitals, we needed more food, we needed more shelter. We put lots of energy into this large segment of baby boomers. And then as we get to 1995, that population is getting older and older, and we don't have as many young people that are there to support that aging generation. So once we get to 2010, the baby boomers are starting to retire, but they don't have as big of a population foundation to be able to support them. So because the birth rates were unusually large for a brief period of time, about 50 to 65 years ago, those age classes appear as a bulge that are moving up the age pyramid. And the younger age classes may not be large enough to be able to support them. And so going back a couple of slides, as we describe these populations, we're looking at the proportion of individuals from each one of the age groups. So we're looking at population age distribution. How does the population curve go? And so these age groupings where we have the baby boomers, or where we have millennials or Gen X or any of those age groupings, we call them cohorts. So here are two vastly different age pyramids. So what we have here on the left-hand side is the age pyramid of Norway. So if you think about what you know of Norway, they are a small Scandinavian country. They're socialist, and they have really good education systems, really good health care. They are an industrialized country. So they appear as a pyramid because you're going to have people being born, and lots of those people, as they're born, make it to old age, and then naturally everybody has to die at some time, so it tapers off near the top. Now, if you look at the difference in the age pyramid between Kenya and Norway, think about what you know of Kenya. It's a developing country. They have a lot of struggle getting food, a lot of struggle getting sanitation, health care, education. So what happens in Kenya is that we have millions and millions of children being born, and the likelihood of them making it to the next generation is unfortunately not so good. And so of all those babies being born, I mean, look at the base here, and then look at the base down here. Of all those babies being born, the chance of them making it to 5, to 9, to 10, up to 20, it's not a very good chance that they're going to be able to survive. And so the strategies for survival in these two different types of country are entirely different. In Norway, they know that the people are going to be taken care of, so they may just have 1 or 2 babies. In Kenya, where you don't know if the babies are going to be able to survive to adulthood, they may have 6 or 7 or 8 large amounts of babies because they don't know if they're going to be able to survive until the next generation. So first world versus third world countries, same as high risk versus low risk societies out there, or environments out there. So as less developed countries become more developed, you start to see that demographic transition from going to look like Kenya to looking like Norway. Because as they begin to develop and get better access to agriculture and sanitation and education, they know that more of their offspring are going to survive, so they tend to have less offspring. So what we call this is a demographic transition. So this demographic transition, looking at birth and death rate, we look at what is ultimately population growth rate, and that's what we're doing in lab this week. So the demographic transition in a pattern of a population growth that is experienced as a country industrializes, if it is characterized by slow growth, like with Kenya, and then fast growth, and then slow growth again, we start to see these survivorship curves changing over time. So if you have slow growth, high birth rates and high death rates, like you see in Kenya, the populations with inefficient systems are going to lead to this slow population growth. And then as they start to industrialize, you still have high birth rates, but then you start to have lower death rates. So as industrialization begins, we have better food production, better health care, we start to have access to reproductive control. So the death rate is going to go down, but the birth rate is going to remain relatively high. Then finally we get to slow growth rate again because we have low birth rates and low death rates. So look at the three different ways that this happens. High birth rates, high death rates. High birth rates, low death rates. Then low birth rates and low death rates. There are three very different ways of looking at similar problems. So population growth is alarmingly slow in Sweden and alarmingly fast in Mexico. Same reasons that we see the growth rate is slow in Norway and the growth rate is alarmingly fast in Kenya. There's a difference because there's a difference in birth rates versus death rates. So at some point, as we have industrialized our nations out there, and as we've gotten better sanitation, better agriculture, better health care, better education, we've seen this exponential growth in the human population. So here what we see, if you look here, this is 0 AD, but 8,000 years BC, we had about 5 million people. And that remained relatively the same as we went to 6,000 BC, 4,000 BC. It's growing a little bit, but not very much. 2,000 BC, we get to 0. Then we start to see that, I'm not sure exactly what this is right here, but as we industrialized right in here, we saw 1850, we jump up to 1 billion people. 1930, 2 billion. Look at how this is going straight up. And so in a very, very short period of time, we've had this population explosion of humans. And so the current birth rates exceed death rates by so much that we added 80 million people to the world population each year. So we didn't even have 80 million people 10,000 years ago. We only had 5 million people that were here on Earth. So this is just an exponentially huge explosion in human population. And so, does the Earth have a limitless carrying capacity? One of the reasons that we've been able to support more people is because we've expanded into new habitats. If you think about Dubai, which is in the Middle East, people wouldn't normally want to live in Dubai. If you think about not having access to skyscrapers or not having good food, not having good sanitation, when all of those things happen, we can expand into places that we would never have been able to survive in before. So with fire, tools, shelter, efficient food distribution, we can survive almost anywhere on Earth. We also have increasing agricultural productivity. So we're making more foods in smaller amounts of spaces that have more nutrition in it, so we can feed more people. And then we're also finding ways to live at higher densities. So it's not just one person living on the flat Earth like we see in the suburbs. In cities, we can have 80 stories worth of people, and we can pack them in to these higher densities because of public health, civil engineering, makes it capable of us being able to survive with lots of people in a very little space. So how high can it go? It's very difficult for us to be able to assess exactly how many resources are needed per person that exists on Earth now. So that's one of the reasons we did the carbon footprint / ecological footprint in the lab, where we looked at how many Earths it would take to be able to survive in the manner that you're accustomed to, looking at how much land you need, how much food and water, how much fuel. So how many Earths are needed to allow you to be able to survive? This is kind of an interesting picture because with assembly lines, we've been able to get resources out to much, much more people. I think that was the end of it. So that's the end of chapter 14. Remember here over the weekend that you should be looking under quizzes for your homework, and you should be looking under the Dropbox to upload your notes. And neither of them are due by Tuesday. I think I have them due. Okay, so that is Tuesday then. Okay, so I made them due Wednesday and Thursday? I made one due on Thanksgiving?
No, they're both due the 25th.
Oh, okay. Then they are both due.
Yeah. It says it's due the 26th.
That's Thanksgiving, right? Okay. Okay, so there's one due Tuesday and one due Thursday. So the notes. Yeah. And most likely you have already done those, but most likely you haven't done the chapter 14 homework yet. I mean, you were here, you took notes, so you're good to go. Just upload them. Do it tonight so you don't forget. I'm not saying that specifically to her, I'm just saying in general. Do it tonight so that you don't forget. I mean, that's easy points. Yes. But not Thursday, because that's Thanksgiving. Yep. Yeah, the post-it note. The notes are due on Tuesday by 4, and the homework questions are due by Wednesday at 5. Yep. All righty. You thought it was what? No, it's just one. It's the November 18th note. And so if you were here, you already have them. If you weren't, then you just watch the video, take some notes, and you'll be good to go. Okay? I am. Oh, that's my dream dog. I have always wanted a golden retriever.
She is probably the most energetic animal I've ever met.
She's so sweet. You haven't seen my Tipsy. My little Chihuahua is about the most energetic pet I could ever imagine. She's awesome. I want your dog.
So for the notes that we're submitting, does that count in the same section as the one quiz did, or is the one quiz 5% of our grade?